Hey, good morning, everybody. This is Mr. Ainsworth, and we are going to get into a really cool activity on graphing polar functions here. So, in Unit 8, we've been studying polar functions or polar points, polar coordinates, and also complex coordinates here, and using and getting used to polar form and all its different ways to really express a number here. And this time, we actually get into functions here, and we learn the qualities and the characteristics of certain functions. And in this activity, we're going to be using Desmos here instead of evaluating, at multiple angles, which would take forever and a day. We're going to use technology, so it's going to be kind of cool. So at the top here, there's a Desmos link, and it's also in Canvas. So if you haven't uh, clicked on the link here and got your Desmos file, you need to stop the video and do that now. And you can see that I have split screen going on here on my iPad here. I've got Desmos on the right using that link that has already been pre-designed for us that we're going to be using throughout the lesson here. So go ahead and get that going. Split screen, have your lesson on one side, your Desmos on the other side, and you're just going to play with these functions here and learn about the different type of graphs that can be created using polar functions. Okay, so here we go. So part one, we're going to go into here. There's three parts, obviously, part one, two, and three. You click on this arrow or this, yeah, arrow key, and then it gives you two functions. If the first one, r equals a cosine theta, is not turned on, you just click on the color and you'll see it appear. And then you can follow the directions here through the activity and kind of just play with the different functions and write down your observations. That's why this is a really cool activity here. Uh, you can learn a lot by using Desmos here because it graphs a variety of different functions pretty easily, assuming that you know how to set it up. All right, so part A here says what is the independent and dependent variable of the function? Okay, our function in this case is r equals a cosine theta. And as you guys know, theta is our input variable, so that's your independent variable here. So the independent variable is always your input variable. And in this case, it is theta. And r depends on theta, so r is your dependent variable. So it's the output of the function depending on whatever angle you put into the function. Okay, it says select the play button for this letter A and watch. What do you notice? Okay, well, here we go. So first of all, we have a circle. So r equals a cosine theta. It gives you a circle right here. But what does A do? What does A do? So we're going to click the play button here, and the slider changes from values from -10 to +10. You just watch and observe. All right, what happens to the circle here as A goes from -10 to +10? If you pause it at any point, okay, you'll notice that from when A is negative, I don't care what negative number it is, okay, the circle's, first of all, it's on the left side of the y-axis, okay, and all of them, no matter what the circle you're looking at here, they're all symmetric about the polar axis, okay? When I say polar axis, I'm talking about the x-axis here. Now, in our lesson here, number two, we're supposed to be graphing r is equal to 5 cosine theta. So let's slide it over to 5. Let's take a look at it. All right, so it's a circle. Now it's on the right-hand side. So when A is positive, it's on the right side of the y-axis. Still symmetrical about the x-axis or the polar axis. And if you take a look at the diameter of the circle, it's 5. All the way up to 10 here. Notice that when A is 10, the diameter is 10. So actually A gives you information on the diameter, and if it's positive, you're on the right side of the y-axis. If it's negative, you're on the left side of the y-axis. Okay, so here we go. Let's make a few observations here. So A, it says, what does A do? It says, what do you notice? Well, A affects the size, but also if A is positive, you're on one side, negative on the other side. So let's write that stuff down. Okay, so A affects the size of the circle. When I say size, I'm talking about the diameter of the circle. That's the first thing that I notice. All right, first thing. Second thing I notice is that if A is positive, the circle's on the right of the side of the y-axis. If A is negative, you're on the left side of the y-axis. So if A is negative, so less than 0, okay, circle is on the left, okay, left side of y-axis, okay, and if it's positive, you're on the right side. So, so if A is positive, greater than 0, we're talking about right side, okay, of the y-axis. That's the first observation right there. And also A is the diameter. So we also know that I'm going to say, let's say the absolute value of A, because A can be negative, right? The absolute value of A is equal to the diameter. That is something I also noticed. Okay, so when you graph these things and sketch these things, you're going to slide the value of A to the proper, oops, to the proper value. Like we have to graph 5 cosine, R is equal to 5 cosine theta, so slide over to 5, and you'll notice that is a circle, symmetrical about the polar axis or the x-axis, and it's on the right-hand side. Okay, so on our little graph here, let's zoom in. Okay, first of all, you have to know that this is typically referred to as the x-axis, but guess what? We're in talking about polar stuff here, so this is called the polar axis. You guys should know that. And then here A is 5. Okay, that refers to the diameter of the circle. Okay, and A is positive. A is greater than 0, so it's on the right side. So I'm just making observations here based upon my experience from Desmos, and then I sketch it. So I got to the fifth circle. 1, 2, 3, 4, 5. Right there, there's fifth circle, and then you sketch it. Okay, it doesn't have to be perfect, just give your best sketch of your circle. Circle diameter 5. Okay, now how about when R is negative 2 cosine theta? Well, you slide it back to negative 2, and notice now you're on the left side. It's a smaller circle with a diameter 2. So now here, A is negative 2, and that tells me the diameter is the absolute value of that. So the absolute is equal to the absolute value of negative 2, which is 2. But because A is negative, okay, we're talking about left side. So I'm just making notes so that in the future, if I see a different function, I can graph it easily. Okay. So again, we go out to the second concentric circle here. That's 2, and then you draw your little circle. Okay, there we go. All right, and then we have to answer the other question. So what similarities do you notice between the two graphs? Well, they both have x-axis symmetry. So both have x-axis, and when I say that, I'm talking about the polar axis symmetry. Okay, no problem there. Just that if A is negative, you're on one side, left side, and if A is positive, you're on the right side. And it says, what differences do you notice? Okay, as I just said, when A is less than 0 or negative, okay, it's on the left side of y-axis. Okay, when A is positive, okay, when that greater than 0 obviously means positive right here. We're talking about the right side. So what I'm doing is I'm making notes of my observations when I was using the Desmos activity. So be very detailed in your observations because obviously the end result of this activity here, you want to be able to graph any polar function on your own without Desmos. So we're using Desmos to obviously learn, but in the end, you want to take what you've learned and you want to obviously graph things on your own. Now, number 3, it says for each of the graphs above, give the order pair and polar form of the point that is furthest away, all right, from the pole or the origin. Okay, so we got to figure out, when is it furthest away? And that's when when cosine reaches its max. Okay, so you get it furthest away. We got to be thinking here. When is cosine theta? When does cosine theta? Not when is, but when does? Okay, when does cosine theta reach a max? Because we're talking about the furthest away, right? So theta equal what? So theta is equal to, let me see, the cosine of the range of cosine. Okay, range of cosine is from -1 to 1, right? And this is the min and this is the max. You guys know that from prior experience. But at what angles do you get the max? And what angles do you get the min? All right, so when are they? So we need to figure that out, right? Let me see. So cosine or theta could be equal to 0. Cosine of 0 is equal to 1, and cosine of pi also. Cosine of pi will give us a max of 1. And so what we want to do is we want to substitute those numbers in and see what happens. So r is equal to cosine, excuse me, 5 cosine theta actually. Let me work with the first function here. So for this function here, r is equal to 5 cosine theta. If you substitute in 0, so in polar form, you have to remember that it's always r comma theta. Right here, if you substitute in 0, what do you get out? Well, if you substitute in 0, cosine of 0 is 1 times 5 is 5, so you get 5. So at 5 comma 0, you're going to reach a max, and that's why the circle here has a diameter of 5. Okay, so that's the max value here. And how about the other function right here? So when you deal with the other one, the other function was r is equal to -2 cosine theta. If you put in 0 there, so we get or pi. Um, so if you put in 0 for theta here, cosine of 0 is 1 times -2 is -2. So you get -2 comma 0 for polar form. Or if you put in pi, let's put in pi just for funsies here. All right, put in pi for theta. Remember, it's r comma theta, so theta is the second coordinate. Cosine theta is -1. And guess what? -1 times -2 is 2. So 2 comma pi. If you go out 2 units and you rotate on this angle here, if you go out 2 units to the right and then rotate pi radians, you end up right there, okay, at that point. That's 2 comma pi radians, or you can say -2 comma 0. Whereas the other one here on the first circle here is just your 5 comma 0. All right. So believe it or not, there's ways to figure out where this thing starts by looking at the max and min of the cosine or sine function, whatever you're dealing with. Okay, number 4. It says turn off the graph of this function. So we're going to turn it off. Just click on the color right here and then turn on the graph of r sine theta. So the second one here. And notice the differences here. So we're going to do the same basic thing. We want to change the slider. So hit the play button here. And watch the a value go from -10 to 10. Now notice that we still have circles here, but these circles are symmetric about the y-axis now. And secondly here, when a is negative, it's below the x-axis, and when a is positive, it's above the y-axis. Okay, and so what we can do is we can make note of that. Okay, so let's do that. All right, it says, what do you think the a value represents? Okay, so the a value here, again, if you just stop it at some point here, let's say positive 10, you'll notice that the diameter of the circle is 10 when a is 10. If a is -10, it's still, the diameter is 10. So remember, the negative sign here just makes it go down below the x-axis versus above the x-axis. So the absolute value of a gives you the diameter of the circle. Okay, so Let's make a note of that. So the absolute value of A is equal to the diameter, okay, of the circle. All right. And then it says, how do the circles um, have the sign in their equation differ from the circles that have cosine in them? Why do you think this? Well, okay, so now sine here, because both of these functions in number 4 have the sine function involved. These are symmetric about the y-axis. So let's make a note of that. They're both symmetric about the y-axis. That's the first thing. And then also A tells you if A is positive. So if A is positive, greater than 0, that's what that means. Okay, it's above the x-axis. Okay, if A is negative, okay, less than 0 means negative, it's below the x-axis, as just stated. So take a look at the, again, Desmos right here. When A is positive, notice the circle's above the x-axis. When A is negative, there we go, it's below the x-axis. But in either case, it's symmetric about the y-axis. All right, okay. Okay, so let's pause this and let's continue. So number 5, for each of the graphs above, give an ordered pair and polar form of the point that is furthest away from the pole or the origin. All right, so when does sine reach its max? Okay, so let me ask you a question. So when does the sine function, sine reach a maximum? So you got to be thinking, okay, so the range of sine is from -1 to 1, and that occurs either at the top of the unit circle at pi halves or uh, at pi halves, or at the bottom of the circle. Well, that reaches its min here. So at 3, well, okay, pi halves here. Let me just answer this question here. So look, being a little distracted, I apologize. So when does sine reach max? Okay, so theta. So theta here is equal to pi halves. I'm going to switch the question. When does it reach a min? And that's at the bottom at -1 or at 3 halves pi. So same question, but you're at the bottom of the circle here at 3 pi halves. Okay, and so it says give an ordered pair and polar form of the point that's furthest away. So for the first function here, for um, r is equal to 4 sine, so 4 sine of theta right here. If you substitute, let's say, pi halves in, again, it's r comma theta here, so I'm substituting in pi halves in for theta. Sine of theta is 1, right, times 4, gives you 4, so 4 comma pi halves. All right, for the other function, for r is equal to -3 sine theta here, if you want to substitute in pi halves, let's go for it here. We're going to get sine of pi halves is 1 times -3 is -3. Or if we substitute in 3 pi halves, sine of 3 pi halves is -1 times -3 gives you +3. So there's 2 points for that one there. All right. And so what happens to the sine, the polar function here, all right, in terms of sine, when you change these values? So let's go through it again. In fact, let's gotta graph these two. So the first function in number 4, let's set the slider to 4. All right, forgot to do that. So notice that we have a circle up there with diameter of 4, symmetric about the y-axis. So I'm going to go up 4 units or 4 concentric circles. 1, 2, 3, 4. All right, we're at 4, and then draw my circle. All right, and again, right through here we have a diameter of 4, and it has y-axis symmetry. And then on the other one here, A is -3, so we're going to slide it over here to -3. Notice it's below, so A here is -3. It's below the x-axis. Just making some notes. It still has y-axis symmetry. So I'm going to go 3 units down, 1, 2, 3, right? And then draw my circle below the x-axis. There we go. So again, the x-axis here, or the polar axis, is the horizontal one. So this is referred to this as the polar axis or the x-axis. And if a is positive, like right here, a is 4 and it's greater than 0, it's above x-axis. And if it's negative, it's below the x-axis. Okay. And when I say x-axis, I'm talking about the polar axis. Okay. Okay. There we go. And again, this is a really cool activity. Desmos is your best friend. You can learn so much by just observation. I've been using this for years, ever since we've had the right technology, meaning to learn and teach in the classroom here. And this right here is the way to do it. You could evaluate a table of, let's say, 15 points and do it that way, which is what we used to do back in the day when I first started teaching pre-calc, before Desmos was around and before we had the technology. But this makes it a whole lot easier. Okay, number 6. Here we go. It says close the folder for part 1. I just did that. Open it up for part 2. And now we're looking at 2 new functions. We're going to take a look at r is equal to a times cosine of n theta. So now we're going to affect the period of the function. And the second one we're going to look at, all right, here's a sine of n theta, where again the period is going to be affected. So what do these look like? Are they circles or are they something else? Well, I don't know. Let's find out. That's the purpose of the activity. So you turn on your function, and holy cow, it's not a circle. Okay, so what in the world does this look like? So with only the first equation turned on, press and play the A slider. What is changing? Okay, so we're going to hit play, and there we go. So this right here is called, okay, a rose. And roses, as you know, have petals. And so we are looking at what's called in mathematics a 3-petal rose. Okay, so now notice the number of petals is not changing here when A changes. Okay, only the length of the petal. Okay, so if I just pause it somewhere. Okay, so notice at when A equals 6, the petal length is 6. Okay, so notice also that the position of the petals does not change. They're symmetrical about certain angles here, and we're going to talk about that. And we'll talk about why and how to find those angles and everything like that too. So, but when A is negative, the petal, one of the petals is symmetrical, or the first petal is symmetric to the polar axis, but it's on the left side. When A is positive, you're symmetric about the x-axis, but now you're on the right side. Oh, okay. All right. Okay, so now that's when we change A. So it's with only the first equation turned on, press the A slider, what is changing? So the first observation is pretty simple. It's just the length of the petal. So let's make a note of that. All right, so the length of the petals. Okay, we're talking about roses here. We call these roses in mathematics, and as you guys know, roses have petals. So we need to figure out the length of the petal and also where it starts and the angle between petals and so on. And that is part of the discovery here. Okay, so it says pause slider A and press play on the N slider. Okay, so let's press play and see what happens. Oh my God, that goes too fast. I'm going to pause that. Okay, so let's start off with, let's say N equals -5. So notice -5 here, we have 5 petals. We'll go to -4. If we count up the petals, we have 8 petals. Ooh. So when N is -5, you have 5 petals. When N is -4, you have double that many petals. So 2 times 4 is 8. 3, when N is -3, you have 3 petals. So it seems like when N is odd, we have that many petals. When N is even, like 2, see, when N is -2, we have 4 petals. It's always twice the number. All right, so let's go to the positive side here. So when N is 2, you have 4 petals. When N is 3, you have 3 petals. When N is 4, you have 8 petals. When N is 5, you have 5 petals. So when N is odd, you have N petals. All right. When n is even, you have twice that many or two n petals. Like here, you have 12 petals. Holy cow. All right, so it says what is changing? So what's changing in number six, part B here is the number of petals, okay? The number of petals. Okay, now based upon what I just said there, we're going to go back here. I'm going to jump to number eight. How can you tell from the equation how many petals there are? Well, I'm going to go back to do what I just did here. So from when A is 1, when A is 2, well, I'm sorry, let's bring it back to, let me bring it back. A is 6. I want to change N, not A. So let's change N. When N is 1, excuse me, when N is 2, even, all right, you have 4 petals. When N is 4, you have 8 petals. When N is 6, you have 12 petals. All right, so right there, I know that when N is even, we have basically two n petals. So we'll write that down. Go to number 8 here. If n is even, number I'm talking 2, 4, 6, 8, so on. Okay, there are two n petals. 2 times n petals. Okay, I'm talking twice as many. Okay, so if n is 2, you have 4 petals. If n is 4, you have 8 petals. Okay, you have twice the petals. Okay, that's what I'm talking about. 2n means twice the petals. All right, now if n is odd, that's not the case. If n is odd, let's go back and let's review. Okay, I'm talking about 3, 5, 7, so on. So let me change it back to 3. Okay, so notice we have 3 petals. Change it to 5, you have 5 petals. Change it to 7, you have 7 petals. So if n is odd, okay, there are only n petals. It corresponds to the n value. All right, that's my major observation right here in the beginning. Now it says change the n and slider, a and n sliders, okay, to correspond to the following functions. All right, so first one here, this is a cosine of n theta, so n here is 3. So n is 3, a is 5, so let's change a to 5. I'm going to change n to 3. Okay, so take a look at what we have here. So on this one here, we have a 3-petal rose. So and then we'll figure out the angle between the petals here in a minute. So we have a 3-petal rose, and notice that it starts. Okay, it starts on the x-axis at the 3 units in. Okay, so what we do when we sketch this here, we can sketch it. We'll also screenshot this. And actually, I can't do that during a video, so I'm just going to sketch here. So what we want to do is plot 3 units to the right. Okay. Not 3 units to the right. I'm sorry. A is 5. So A is 5. There's your petal length. So A is 5 right here. N is 3. All right, so we're going the 5th circle out. So 1, 2, 3, 4, 5. Plot, okay, and you can draw your first petal. There we go. Now at 2/3 pi, we have another petal. So if you guys remember your thirds here, this is pi thirds, and this is 2 pi thirds over here. You get your next petal at 5 units out. 1, 2, 3, 4, 5. All right, and you draw your next petal. Now, when you graph this thing, it doesn't graph one petal at a time. It does one half at a time. It's kind of unique, and you only see that and really understand that when you actually plot a bunch of values, and you can see them plot as you go. So let me plot 4/3 pi here. So look at the graph right there. We want to go 5 units out. 1, 2, 3, 4, 5. All right, and then draw our third petal here. So there's your 3-petal rose. Okay, and what's the angle between petals? Well, the angle, if they're all equally spaced apart, okay, all petals, okay, are equally spaced apart. If you know that, which now you do, okay, what we do is we take 360, or you can take 2 pi divided by 3, and they're 120 degrees apart. Okay, and that, or you could say 2 pi, 2/3 pi radians apart. That's the angle between them. Okay, so I'm talking about from here all the way to here. This is 120 degrees apart. So in between every petal is 120 degrees apart. Does that make sense? Okay, so now what about the second one? The second one is going to be a little bit different because you have A is negative here. So A is negative on this one. So A is -4, N is 5. Okay, and it's odd. Likewise, the previous one was odd. That's why we only have 3 petals on the first one. We expect 5 petals here, so we expect that. And then, but A is -4. Ooh, so it's the first petal is not going to start on the right side. It's probably going to start on the left side. Let's figure it out. So I'm going to change A to -4. All right, change N to 5, and we'll see what happens. Okay, and what I said was correct here. So check this out. Look at that. You can zoom in right there. So the petal length now is 4. So A is -4. There's your petal length. So take the so since A is -4, you take the absolute value of that, and you get your petal length. Petal length is equal to 4. But this time it starts. We got to go 4 units left. Okay, so let's do that. So we go 4 units out. 1, 2, 3, 4. There's 4 right there. And this one's a little bit harder to draw because we have 5 petals, and the angle between the petals is 360 divided by 5, which is 72 degrees. So this one's a little bit more difficult to do in your sketching. You'd have to approximate that angle. But let's draw the first petal right there, and then you have to go 72 degrees. Okay, 72 degrees, which is maybe it's less than 90, so I'm approximating it to be right about here. Okay, and another 72 degrees, so 72 and 70 is 144, which, let me see, so that's got to be over here somewhere, probably right about here, so I'm just estimating. All right, and then another 70. Again, you just keep on rotating 72 degrees, stay on the same circle. And then another 72 degrees on the same circle, and they're equally spaced apart. So there's your 5 petal rows. Okay, and again, the angle between them from here to here, all right, 72 degrees apart. And this one here, we started here because A was -4. So you start on the left side, okay, of the x-axis instead of the right side. So when A is positive, like here A is 5, on the first one here, you start on the right side. And when A is negative, you start on the left side. I'm talking about the x-axis here, or the polar axis. And you're going to see that happening in all these functions here, no matter what you do when you change a function. Okay. Now here, and for the third one here, A is 5, but N is 2, and that's even. And as we observed earlier, we should expect 4 petals. So here, let me write down 4 petals, and then I'll verify that here in a minute. So we're going to change A to 5. Let's go back to 5. And then N is 2, so let's slide it back to 2. And you'll notice that we have a 4 petal rows. Now the angle between petals is 360 divided by 4, or 90 degrees, which makes sense. And I'm talking about pi halves radians. So this one's a lot easier to draw here because this one starts on the x-axis. Okay, so we go or 5 units out. So 1, 2, 3, 4, 5. Okay, and then you go up 5, and then left 5, down 5, same circle, and you draw your petals. And you'll notice how I'm drawing them now. This is actually how it's done. Okay? All right, and one more. Let's do another one. So here, n is 4, so that's even. So I expect 8 petals because you double. So even, you double. So 4 petals. A is 3, so that's the length. A is 3, that's the length of the petal. And so let's verify that. So I'm going to change A to 3. All right, and then I'm going to change N to 4, see what happens. So you'll notice that we have 8 petals right here. Okay, and you take 360 divided by 8, all right, you get 45 degrees or pi force radians in between them, okay? I'm talking about the angle between the petals. All right, starting on the x-axis. All right, so let's go for it. So here we're going to go 3 units out. So go to the third circle here, and then now these polar grids do not have the 45 degree marks labeled, or I'm talking about pi force radians, so you're going to have to mark them. All right, and it's obviously half the distance between 0 and 90, and between 90 and 180, and so on. So you should know where multiples of 45 degrees are. So here we go. So I'm going to mark my points where the end of the petals are first, and then I could sketch my graph. Okay, so those are the ends of the petals. So here we go. No, these are thinner. Now, I don't know if you noticed how I graphed that there. That's kind of how it works, believe it or not. If you actually graphed it by using a lot of points, you would see the curve generated like that. Okay, we're learning. Here we go. Number 9, what does it say? Evaluate each of the equations at 0. What do you notice? What does this tell you about where the first petal is located? Okay, so let's go ahead, and we're talking about the first petal location. So what are my functions? Okay, so at the top of the screen are my functions. So here we go. So r is equal to, on the first one, 5 times cosine of 0. Cosine of 0 is 1 times 5 is 5, so r is 5. Okay, next function. So r is equal to negative 4 times cosine of 5 times theta, so times 0. Cosine of 0 is 1 times negative 4 is negative 4, so r is negative 4 here. And the first one, r is 5. Next one, r is equal to 5 times cosine of 2 theta, so 2 times 0. 2 times 0 is 0, cosine of 0 is 1 times 5, so we get r is equal to 5. And my last one there, r is equal to 3 times cosine of 4 times theta, so 4 times 0. Cosine of 0 is 1 times 3 is 3, so r is 3. Right here, so the radius is always the a value when theta is equal to 0. So let's make a little note of that, okay? Now the radius, I'm talking about r here. Radius r, all right, is always the a value, all right, when theta is equal to 0. Okay, there we go. And that's the tip of the petal. Okay, so let's make a little note of that. Tip of each petal. All right. Now, number 10, we're going to switch. Okay, so now we're going to be switching to the different function, and now we're going to turn off this function and turn on the other function. Okay, so There we go. So now we have the sine function, and let's go through the different facets of your sine function. So this is number 10. All right. Turn off the cosine function, turn off a sine of n theta, change the a and n sliders to graph the following functions and indicate where the first pedal starts. Okay, here we go. So is number 10. All right, so 5, let's change. So a here, a is 5, n is 3. So a is 5, there's your, let's see if that's still the pedal length. So let's change a to 5, and let's change n to 3. Where's my a? Where'd it go? Oh, it's right at there at the top. Sorry, guys. Okay, so a, gotta get straight here. So a is 5. There's 5. All right, and then n is 3 in this case. Let me change it to 3. I get a little crazy right there. All right, so there we go. We have a 3-pedal rose again, but now it looks totally different than our 3-pedal rose earlier. Look at that. So the starting pedal position and its symmetry is totally different than cosine. So you have to understand the differences here. Okay, so here, this one here, notice is symmetrical about the y-axis and not the polar axis. So let me put that in red here. So let's zoom in on our first one here. Here's the y-axis. So this has y-axis symmetry. And notice that it has A is still the pedal length. So when A is 5, okay, we got a pedal length here of 5. So that's cool. That doesn't change. And again, N is 3 is odd. All right, and we have 3 pedals. So that doesn't change, but the symmetry changes. Okay, so that's cool. So we can still use what we've learned earlier, but we have to modify the symmetry. Okay, so here we got to go down 5 units. So go down 5 units. 1, 2, 3, 4, 5. And then at pi 6, this is pi 6 over here. It's on the same circle. And then at 5 pi 6, just look at Desmos off to the side. This is 5 pi 6 over here. You're on the same circle over here. And these are your pedals. All right, so here we go. Got to put the sound effects in. Okay, there you go. There's your 3-pedal rows right here. And the pedals are pi 6, 5 pi 6, and then 9 pi, or it's 3 has 5. Okay, down at the bottom. All right, and again, uh, there you go. So we have y-axis symmetry here, and the angle between pedals is 360 divided by 3, or 120 degrees. Okay, so this angle right through here between the 2 pedals is 120 degrees apart. Okay, they're always equally spaced apart, so you just take the number of pedals divided by, 360 or 2 pi and divided by the number of pedals. That's how you do it in general. Okay, now the next one here, A is 3 and N is 5, so let's go ahead and let's see, 5 is odd, right? And so that means we have 5 pedals. Okay, so let's change A to 3 now. That changes the length. Increase N to 5, and so notice that we have a 5-pedal rows here, and notice it still has y-axis symmetry, which is cool. Okay, so check that out. All right, but the first pedal does not start on the x-axis here; it's off the x-axis. So we're gonna have to figure out how to do that. So so the angle, let me see, angle between pedals here, same thing. So 360 divided by 5, that's 72 degrees. That's gonna be fun. All right, but we're gonna go up to the, so the A is 3 here, so the pedal length, so length 3. So starting on the y-axis, again, these have y-axis symmetry here, so I'm going to draw this in red so you can see the symmetry. So y-axis symmetry. And then the first pedal is 3 units up. This A is 3, so I'm going to go 3 units up. So 1, 2, 3. And then I have to approximate the other pedals where they are. So it's going to be just looking at your Desmos graph over here, off to the right. Got to be on the same circle. I'm approximating right now, you guys. I'm looking at Desmos over here off to the right, and I'm approximating the position of my petals so I can give it my best sketch. There we go. And again, the distance or the angle between petals, right here to here, is 72 degrees in this case because they're all equally spaced apart. All right, next one. What do we have? We have A is 5, N is 2, and 2 is even. So I'm expecting twice as many petals, so let's make sure we get that many, right? And so let's change A to 5 now, and then N, slide N back to 2. And notice that we have, there we go, we have 4 petals, but notice they don't start on the x-axis like the previous one did. See, look at that. On cosine functions, they'll start on the x-axis. Here, not so much. This one starts on the 45, okay, right here. So at 45 degrees or pi force, we should write it in radians. We should be good at that. So actually, it doesn't matter. Both of them are good. So pi force radians, there we go. And that's, so we're going to mark that. I'm going to mark here at 135 or 3/4 pi, and then down here at 5/4 pi, and then 7/4 pi. I'm going to mark these off. So 135 is the same thing as 3/4 pi here, as you guys know, radians. And then I've got to go, let me see, radius is 5. Excuse me, A value is 5, the length is 5. So this is the length. Okay, and now I can plot some points. So I'm going to go out to the 5th circle here, 1, 2, 3, 4, 5. Stay on that circle. Go all the way around. Just stay on your circle. The same circle, that is. And that way you can sketch your graph. Okay, so here we go. All right, so here the angle between petals is 360 divided by 4, or 90 degrees, or pi halves. So this angle between these petals, I get 90 degrees, or pi halves radians. Okay. Okay, and then here we go. And then the last one here, A is 3. So A is 3, N is 4. And guess what? That's even. That tells me that we should have 8 petals by observation. So I'm going to change A to 3. So back it off to 3. Increase your slider to 4, and watch what happens. You have 8 petals. Holy cow. And then 360 divided by 8, that's 45 degrees, or pi force. That's the angle between them, but it doesn't start on the x-axis. Okay, this one, if you look closely here, it's going to be less than 30 degrees. So here, well, in general, just so you know, it's going to be the first petal always starts at whatever pi divided by 2n is. Okay, so first petal, let's do this. First petal starts, okay, at whatever pi divided by 2n is here, and n here is 4. So this is equivalent to pi divided by 8. And that's the same thing as 180 divided by 8. What is that? So let's figure that out. So 180 divided by 8, that's about 22.5 degrees. Okay, so 22.5 degrees. And that, if you look here on the graph here, that makes sense because pi 6 is 30 degrees and it's less than that on the first petal in quadrant 1. Okay, so on this one here, you're going to have to approximate it. And the pedal length here, A is 3. That's your length of the pedal. So we got to stay on the third circle here. And we have to start at 22.5 degrees. So I'm going to go out to the third circle, mark off, let me see, this is 30 degrees, so maybe 22.5 is right about here. 22.5 degrees. So third circle out, 1, 2, 3, right about here. Okay. And then you have to add 45 degrees and go all the way around. So just approximate it right now, looking at your graph there in Desmos here. So the next one here is probably going to be approximately right about here, and then roughly here. Again, I'm looking at Desmos here to do my approximations. So I expect you guys to do the same thing, just approximate right now, because this is not the easiest thing in the world. Okay. All right, here we go. This shouldn't overlap. I made one of my pedals was not good. Okay, so whatever you do, don't overlap your pedals. Okay, if I was not running a video, I'd probably redo that. Okay, so don't overlap pedals. If you notice in Desmos, uh, it doesn't happen like that. Okay, so if you have to redo your sketch, you know you're on an iPad too, so redo your sketch. Do not overlap pedals. Okay, number 11 and 12, and then we're going to be ending the video here. Okay, what similarities, differences do you notice between the equations of cosine in them versus equations with sine in them, shape, center, and location, etc. Okay, so if you compare these two, the top graphs are dealing with cosine, the bottom graphs are dealing with sine. So cosine, let's write this out. Cosine has x-axis symmetry. So the cosine graphs, they all have x-axis symmetry. Major, that's major, okay? And secondly, okay, they always, if you look at them again, have the pedal on the x-axis. So if you look at the top graphs there, their first pedal starts on the x-axis. So always has first pedal, okay, on the x-axis. Okay, the sine functions, they're different, right? Okay, they have y-axis symmetry. Okay, and then has a pedal on the y-axis. Okay, there's always one pedal. Okay, always one pedal on y-axis. All right, when n is, ooh, I gotta be specific here. All right, when n is odd. Okay, not even. So when n is odd. So I got to qualify that. Okay, because it changes. When n is even, it's a little bit different. Okay, as you can tell in the third graph. Okay, so in number 12, last one here, for each of the four graphs, how can you determine the angle between the number of petals? I did that many, many times. Okay, so they're all equally spaced. Okay, so since petals are equally spaced, and I talked about that already, equally spaced. Okay, the angle, all right, is found by taking 360 divided by the number of petals. Okay, or you can take 2 pi divided by the number of petals, if you want it in radians. Okay, and there we go. So I'm not going to spend time in this video summarize everything in the quick notes. All right, everything that you need to know is all through here in this first 2 pages of the lesson here. So hopefully you're going to be back in class and we can work together then. But again, the key to this is practice, so make sure you do your homework. go through the check for understanding here and start your homework on the lesson to practice what you've learned. And then, of course, you can graph things in Desmos to verify what you've learned. So hopefully that helped you out. All right, this is Mr. Ainsworth here, and I'm at Great Oak High School. Been teaching there ever since the beginning of the school back in '04. And again, do yourself a favor and just work hard, practice, do your homework, and I'll see you then. Take care. Bye bye.